Hello. I wanted to make this video to introduce a topic that I think is very difficult to get into, and that's elliptic integrals and elliptic functions, but we'll start with elliptic integrals. So this is going to be about doing an integral that Mathematica can't do, but with Mathematica. Um, some of the resources that I used are referenced here. NIST, they have an online digital library of mathematical functions. Bird and Friedman has a handbook of elliptic integrals. Pierpont is an old book, but it has a good description of the process that we're going to go through. Hancock has two books that are very good, and they have 3 volumes of books. And there are many, many others that delve into these topics. So elliptic integrals and Jacobi elliptic functions, and there are related Weierstrass sigma functions, Weierstrass zeta functions, Weierstrass p functions, theta functions, Weber functions, Ramanujan G, big G and little g functions, Dedekind etas, elliptic lambdas. There are all sorts of elliptic functions, and it's a mind-bogglingly vast area of research. It evidently dates back to 1655 with Wallace's attempt to find the arc length of an ellipse. And since then, people have been using it and working on it and building this theory. And mathematicians, including Euler, Gauss, Abel, Jacobi, Poisson, Hermite, Kronecker, Poincaré, Legendre, D'Alembert, Weierstrass, Ramanujan, Dedekind, many more have been working on it. So there's a lot of work, and it seems very difficult to get into, and it's hard to figure out where to start. So I wanted to mention in Mathematica, they have a few guides. For example, they have all of these elliptic functions. There are some tutorials from the mathematical functions guide on elliptic integrals and elliptic functions, and just a smaller guide on elliptic integrals. And that's why this is much more approachable. It's a smaller way of getting, and in an earlier way. Legendre did this earlier than Jacobi. So I've chosen to start with elliptic integrals, which they seem to be the most direct and perhaps the most useful because it's just a way of doing integrals. But I want to leave you with 2 interesting facts that could entice you to look into the other areas of Jacobi elliptic functions. And that's this. The first is that every single-valued analytic function which has an algebraic addition theorem is an elliptic function, or a limiting case of one. So this was shocking to me. It's just amazing. But for example, let's take a addition law like the cosine of the sine addition formula. So sine of u plus v, sine of u times cosine of v plus cosine u sine v. This is an algebraic addition formula. You can eliminate cosine in order for sine, and you can also get rid of the square roots by squaring. For example, here I'm just doing some manipulation, but basically you can square it, and you can, solve for the square roots, square it, and you get this expression, which relates the signs in an algebraic way as opposed to a transcendental way. And this is an addition theorem. Similarly, another example is the Jacobi Sn elliptic function, and this is the relation between the Jacobi Sn and the Jacobi Cn and dn. But just like the sine, the Sn, the sine, cosine, and tangent, there are also relations between Sn, Cn, and dn, so you can actually eliminate this. So that's one interesting thing. Another interesting thing is that a Jacobi elliptic function is the solution to the following nonlinear differential equation form that comes up all the time. And this is nonlinear because the dependent function is raised to some power, as well as the derivative is squared. So y dot squared equals alpha y to the fourth plus beta y squared plus gamma. So this is the fourth order polynomial, and the solutions of these are Jacobi elliptic functions. Sometimes, though, Mathematica has trouble with these. So for example, here are two differential equations for the Jacobi Sn and Jacobi Cn functions. K is a parameter and Z is the variable, but you can see this is a fourth order, this is also a fourth order polynomial. The first Mathematica is fine with if I just evaluate ODE1 and do desolve on it, it comes back with the Jacobi Sn functions. But the second one, it gives me a sort of more let's see. Okay, it gives you a, oh, hold on, I have to, K is something. Sorry about that. So ODE2 comes up with something much more complicated, inverse of elliptic functions. So, but it can also tell that ODE2 is a solution. So if I plug this back into ODE2, you can see that it comes out to be true. Okay, so going back to the original script, more generally, as we'll see below, elliptic integrals are related to the solutions of these general cubic second-order nonlinear differential equations like this, or if you multiply by y dot and integrate once, you can arrive at a solution to this quartic differential equation in quadrature, basically by separating and integrating. So for example, you can separate this, take the square root, solve for dy, solve for t, which you can say is the independent variable, integrate it, and you get something like this. So we need to know how to do integrals like this. So then after that, all you need to do is invert for y, but that's sometimes difficult. So how do you do these integrals? Well, here's the definition of the elliptic integrals. There are actually many ways of defining elliptic integrals, but these definitions will suit us. They're called the Legendre normal forms. The incomplete elliptic integral of the first kind is given by f, and it's the integral from 0 to x of this expression, which if you recognize is a quartic in t, where k is called the modulus. So for example, in Mathematica, I can try this integral out, and it comes back as an elliptic f with the argument pi over 3 and 1 over 49, which is this squared. So you'll notice right away that Mathematica uses slightly different notation from ours, but it's equivalent. So in Mathematica, it uses phi and m, which is the square of k, whereas this notation uses sine and square root of m, and I use the semicolon in order to identify the two, but they're basically the same. You can relate the two of them. When the limit is 1, so instead of sine of pi over 3, this is an incomplete integral because we have an unevaluated upper limit. When the upper limit is 1, then it becomes the complete elliptic integral of the first kind, k, which is given by this, and the modulus again is 1/7, or m is 1 over 49. And this evaluates to just a number, so you can see it's about pi over 2. Okay, so that's the first elliptic integral, the first kind. The incomplete elliptic integral, the second kind, is e. Again, it's just given by this expression. And if you multiply the top and the bottom by the square root of 1 minus k squared t squared, you get a very similar form to this, except you have a quadratic on the top in t. Oh, yeah, that's right. So for example, this is an example. This gives you elliptic E. And again, if you take the limit to be 1, this becomes the complete elliptic integral of the second kind. So if we evaluate this, you get all this junk, which, again, it's not what's expected, and it's unfortunate. But sometimes this is what Mathematica gives you, which is why you have to be careful with it. It gives you about 1.5627, and with a very negligible imaginary part. And you can see if I evaluate, it knows what the elliptic E is. So if I evaluate this, you can see that it's the same. So somehow there are transformations between the F's and E's and K's that will allow you to rewrite this expression in terms of this. But so this is still correct. It's just there are transformations to relate the two. So you can see that Mathematica has problems with these things, so you have to be careful. Finally, there's one more elliptic integral, and that's the incomplete elliptic integral of the third kind, which is pi. The parameter is n, and the modulus is k, and you can see this is a even more complicated expression in terms of t. And so, for example, if you evaluate this, you can see that it'll come out as this expression. Again, there's a Mathematica chooses to put this negative sign in here, and I don't know why it does that, but you can see that in this particular case, there's a symmetry that allows us to write it as just the direct elliptic pi, where the parameter is 1/3, which is right here. K is 1/7, or m is 1/49, and the argument is pi/3, or sine of pi/3 in the other notation. So, and again, there's another complete elliptic integral of the third kind, which is just where the value, the end point is 1, and this evaluates fine. So one of the questions is, when is an integral an elliptic integral? And there's a wonderful notion about elliptic integrals, is that you can determine from the outset whether an integral will be an elliptic integral or a linear combination of elliptic integrals by looking at the form of the integrand. And so this is a general form where the integrand is a rational function. Phi is a rational function of its arguments x and square root of p. And p is a polynomial of degree 3 or 4 with no repeated roots. And little c is a constant. So here's an example. A0x is a polynomial in x. A1x is a polynomial in x. A2x is a polynomial in x. Square root of p of x and is a polynomial of degree 3 or 4. And you can see this is sort of the general form for a rational function of x and square root of p. So it's an amazing fact that, this is a very general form, but the amazing fact is that this integral of phi will in general be a linear combination of only those 3 elliptic integrals that were defined above, and no more. So you can reduce it to just those 3, which is just amazing. So it seems simple enough, but this may be a little bit confusing when you look at it, and it really is. It's kind of a confusing set, and you think, well, what integrals actually fall into this category? So we'll take a look at some of them. So here's some examples. Here's an example integral. Again, this you can just try it with Mathematica and see if it works. This is an elliptic integral. So it is an integral where the square root of a quartic, where each of the roots is different. And if you just evaluate it, you can see that it is an elliptic integral, the first kind. So that's encouraging. It works. Here's another example. Mathematica says this is so, but it doesn't seem to fit from what I can tell. So there must be some sort of transformation, but I had a hard time making this explicit. So I have to take Mathematica's word for it. So, but it's an elliptic integral f, a combination of elliptic integrals. This is not an elliptic integral. It is, you can tell that there are too many square root of linear terms. So this doesn't work at all. And even if you try to play around with this, there are just too many, and Mathematica gives it back as a unevaluated expression. And so this is an elliptic integral, and you can tell the difference between these two because one of the roots is repeated, which makes it a polynomial that comes out, and then it can be written. These two terms can be, you can multiply on the top and the bottom by square root of x minus 5 and square root of x minus 6, and it becomes a quartic on the bottom, and everything works fine. So here's this expression. This is not, again, this is perfectly fine. This will come out, but then there's just too many terms that makes this a fifth order polynomial on the bottom. This is, but you can see that these are two repeated roots, so everything works out. This is a cubic polynomial under the square root on the bottom once these are simplified, and you get elliptic integrals. Let me see. So is this one, because you have repeated roots. This is a quartic polynomial and another polynomial at the top. And let's just focus on this last one. This next integral Mathematica can't do, but it is an elliptic integral because it is a rational function, in this case of y. This is the square root of p, which is the polynomial under the radical, and it will, so this should be an elliptic integral, but Mathematica doesn't know what to do with it. So can you trust Mathematica? I think you can, because when it gives you an answer and something to test, you can try it. But when it returns the integral, you may have to do some work in order to find it. So that's what we're going to try. We're going to try to do some work in order to do this integral. Okay, so this is an example procedure to reduce the elliptic integral. And it's hard because it's sort of no wonder why this has gone out of fashion, because it's such a complicated form. You have to, when you're reducing it, it takes so many steps to get down to the point where you could write it as an elliptic integral. Whereas something like, you know, a gamma function is much easier to put your form into a, you know, gamma function form, or, you know, an exponential integral or something like that. Okay, so let's look at some general considerations. First, we assume we have an integral of this type where phi is a rational function of x and square root of p, where the p polynomial p is third or fourth order in x. Smaller orders, I think, are integrable, and larger than that, you get hyperelliptic integrals. But a rational function is of a form a, which is a is a polynomial of x and square root p and b. And the coefficients in this polynomial look like something like this. The monomial terms look like this, some powers of this. The first consideration is that if the polynomial p is of third order, it can be made into a polynomial of fourth order by rewriting the variables. So this is kind of interesting. So if it's third order, you can make it fourth order, and then you can reduce it to something you know. So for example, if you take a to be one of the roots of the cubic equation, you can use this substitution to rewrite the expression. So for example, let's say you have square root of p as this, x minus 1, x minus 2, x minus 3, and you want to rewrite this as a quartic. One way to do this is choose one of the roots. Let's say you choose 1, x equals 1, and rewrite this and choose this as your transformation. So x minus 1 equals capital X squared, and rewrite little y, which is the square root of p, in terms of that. When you do that, you see that capital X is now a 6th order polynomial, but you can see that you can factor out at a capital X squared. And when you take the square root, you can see that this comes out, and now you're left with a quartic in the new variable. So then, when you get an integral of this form, phi of x and square root of p, you can get a 4th order polynomial by doing this transformation, and your new polynomial in x becomes capital X squared plus 1, and your new polynomial becomes x, and there's a quartic. And then this is just the transformation Jacobian. So if you have a polynomial of a root 3 of order 3, you can make it order 4. Second thing to think about is you can assume that you have a polynomial of degree 4 with no double roots, because double roots could come out and then it would be integrable with simpler functions. So for example, here's a double root of 2, and you can see that this integrates to arctan, hyperbolic arctan. So one way to simplify things right away is to arrange the numerator and the denominator with respect to y to form this, the polynomial. Sorry, this should be script y. Phi is equal to a plus b y over c plus dy, where a, b, c, and d are polynomials of x. And you can always do this because y squared is a polynomial of x. So the higher powers of y will eventually get factored into a. So you can rewrite it as this. And then once it's in this form, you can start eliminating problems and dealing with the integrand. So let's pick an example to work through, and I chose the last example that Mathematica couldn't do to try it. This is a procedure that I found in Pierpont. So let's try this integral. It goes, just to be specific, we go from 5 to 6 of this integrand. Again, there's a polynomial on the top, polynomial on the bottom, and here's our square root of the polynomial, the 4th order polynomial. So it doesn't do it, but, and you can see it's a very tame integrand, so it should have a perfectly valid integral. And just to be specific, you can integrate it from 5 to 6, and you get the number 0.146428. So we'll have to remember this because we're going to be checking along the way just to make sure we didn't lose something. So 146428. So we'll come back to this. The first thing you do is a bilinear transformation to shift these roots around. And you use this transformation y equals a plus bx over 1 plus cx to transform these roots. And you want to do it in such a way, you want to find an a, b, a c, and a k to mold the integrand such that you get something, you have this y minus y1, y minus y2, y minus y3, y minus y4, and the square root of that. And you want to get it into this form, which is much more conducive to elliptic integrals. So you want a difference of squares and a difference of squares. So this is done in Pierpont, but basically first you choose your ordering for the y1, y2, y3, and y4. Once you do that, you get a rho squared. This you can evaluate directly. And a sigma squared. You can evaluate these two directly. Then from that, you can compute C, you can compute a from c and the roots, and b from c and the roots, and k from rho. And then m is given by this expression of k in the roots. So choosing a different ordering of the y's will give you a different transformation, and you can play around with it. But you pick one that will give you a good transformation, and which will also give you the modulus, the elliptic modulus that's between the range of 0 and 1. That makes things a lot easier for you. And Pierpont gives other transformations as well. So let's pick this transformation. Y1 is 3, Y2 is 1, 4, and 1. And if you evaluate this, you get rho, sigma, C, A, B, K, and M. And if you just evaluate these are the numbers. So K, if you look at K is 1/3, which is between 0 and 1. Here's A, B, and C. And those will be, and M is over here. So those will be used in rewriting the integral. And but you could choose a different permutation. There are actually 24 ways of choosing the different transformations, and you can find the right one. So let's just do a quick integral to test this. Think of this as a simple integral just so we can get a handle on it. So for example, this is the same integral 1 over the square root of this quartic. And let's try this. So the numerical value of this integral is 1357. Here are the transformations. The new limits of the integration are given by x min, which is 5. So before it was going from 5 to 6, now it's going from 5 to 7. And so now the transformed integral looks like this, 1 over m, and that's the beauty of it. So this works out. It's the same number as before, 1357, 71. So there's the transformation. So it seems like all you need to do is plug it into the integral and you're done. And that would be true, except you have to remember, so this is what you get if you just plug it directly in, and it's not exactly the same. There's off by a factor of 2 here. And you have to remember that the Jacobian of the transformation is 1/2, so you have to include that as well. So there's the 1/2, and then you put in the transformation directly, and you can tell that it's the same. So this just checks the same. This checks it, so this is true. So let's go back to the original integral and do this, and put this transformation in, and that will simplify this quartic on the bottom here. So here's the original integral. Remember, it was 1464/28. And we want to include the transformation y is a plus bx, and we'll get a new expression in terms of x. So again, I have the Jacobian, which is 1/2. I plug in this expression, and I get this form for the new integrand. And the new limits of integration, again, are 5 and 7. And you can see that this actually does factor correctly. If I take this and factor it, you can see that it factors very nicely into x squared minus 1 and x squared minus 9. So let's check the integral. So I put this is the original integral, and I take, this is the new integrand with the factored form, and the new limits of integration are x min to x max. So now we need to do some gymnastics to split this up. And we do that by just reducing using partial fractions. If we could reduce the denominator to a polynomial, then we can split it up, and that's what we're going to do. So the transformed integral is this. Again, the radicand is a factorable, and I'd like Mathematica to be able to do this kind of manipulation, but I haven't been able to figure out how to do it. So let's call our square root of the factored form y. I'm sorry for reusing y. This is unrelated to the integration variable above. we can clear the denominator by multiplying both the top and the bottom of this by y, by the conjugate of this, so 4x plus 4 times the square root. So that's what you get here. If I multiply the top and the bottom by 4x plus, you get this expression with y squared, which I don't want it to evaluate yet. And if you plug this in directly, you get this new form, which is much better. Y, again, is the square root of a quartic. And now we can split this up in terms of a rational function. So when we do that, you get x squared plus x over this expression, which we'll deal with separately. And then you get another expression in terms of the square root. So we're still working on just the integrand right now. If you multiply this last term by y over y, you get an expression that gives you a y on, okay, no, I'm sorry, I multiplied by y squared. Let me see if this is, okay. Oh, this is right, yeah. So if I multiply by y squared over y squared, sorry, let me put that in there. Y squared over, so if I have y squared over y squared, then this y squared is a polynomial of x, and this y and one of these y's cancel, and you left over with one y on the bottom. And so when you do that, you get a rational function in x, another rational function of x times 1 over y. So it looks like, originally we had e plus f times y, but then if you multiply by y squared over y, you get the expression e plus g over the square root of p, where this is the y. So now e and g are rational functions of x. So that now we can break these things up. So here's the full integral. Again, we broke it up some more. So here's the rational function and then another rational function times this quartic polynomial in this expression. And now we call this integral I, and just to make sure we didn't screw anything up, let's evaluate it directly, and you can see that's the same thing, 1464/28. So this integral, let's call it I, is going to be the sum of several integrals, as we'll see below. So there's I1, it's going to be the integral of this, I2, I3, I4, and then there's going to be several in I4, where AI's are constants. So the first term we can integrate directly. So let's see what this looks like. I1 is the integral of this, which if you look at it is just arctangent, and it's integrable. So in fact, and you can see if you do it, evaluate it from the maximum, from the minimum to the maximum, you can see that it's about 0.02 of the 0.14. So we're left with I2 plus I3, which is the rest of this integrand. And the integrand is, again, this is g divided by y, and we need a way to split this up. So again, this is just checking to see whether we're right, and we still are. We peeled off one part. Now let's look at this rational coefficient g and try to break it up. If you try to break it up in terms of, you'd like to break it up in terms of partial fractions, which means each term is a single term, like 1 over, proportional to 1 over x. But this is not quite what a part does. It does, okay, it splits off a quarter and x over 4, but I want to break this up even more. So let's call this something else. Let's call this G1, and there are a bunch of ways you can do this, but one way we can try is by using a Lorentz series. And this is a little tricky. but I think it's kind of neat. But the general ideal is to peel off terms by expanding around a root of the denominator, say right here, one of these roots, and find the residue there. And that is the term, that coefficient of the term in the partial fraction expansion is the residue. And that needs to be subtracted, and you can try the process again. I'll just show you. So there are 4 roots of this. Again, it's a different form. It's a different quartic than before, even though it looks similar. This quartic is it's different. This is what it looks like. X to the 4th minus 10 plus 9, whereas this one's slightly different. 9 minus 11 plus 9. So anyway, so you take G1. These are the roots. There are 4 roots, and we'll call them R1, R2, R3, and R4. And then what I want to do is I want to find the residue of G1 at R1, and that comes out to be the coefficient alpha 1. Then I want to take G1, which was this expression above, subtract off this term that was the residue and the partial fraction part of it, and then do it at another root. Find the residue at another root, say R2, and that gives me alpha 2. Subtract off the alpha 1, the R1 term and the R2 term, and then do it again. You get alpha 3, and then the 4th one you do. You could just leave the rest of it alone, but just to get it into the right form, the residue of G1 subtracting the first term, subtracting the second term, and the third term, find it R4, and this gives you the 4th residue. So if you don't trust me that this works, I can show. Here's the original rational function, and this should be equal to the sum of 4 broken up parts, and this is true. So now we've expressed G as 1 over 4 plus x over 4 plus this rational function G1, which a part gave us. Then we can break this up further to give us this sum of 6 terms. And the roots alpha are the residues of G1, and the roots Ri are the polynomial this. So we have to remember those when we finish up. So this is equal to this, just it's a mess, but it's broken up into pretty nicely soluble parts. This just checks the full partial fraction, and it's true. And you remember in the integrand, this is all integrated, multiplied by 1 over y, because g is this rational function coefficient. And now we need to handle these integrals. So the term x over 4 is actually integrable. This is going to be I2. If you integrate this, this becomes an arctanch. There's a side note. This was different in version 11. This gave me, instead of arctanch, it gave me logs. And I thought that was surprising, and I tested it, but they're the same, and so so this must just be the way that they evaluate the integrals now. But I thought it was interesting because it led to some interesting integer identities, such as this, which I think is fantastic. It's an integer identity that's correct. Anyway, there are no terms in this that are proportional to 1 over x by itself without a root, but there could have been, and those are also integrable. For example, this is integrable. It becomes logs. All right, so let's check to see if we still have the same number. If you integrate this, I1 is the first part that came out. I2 is the integrable part. We still have this 1/4 in here. And again, we get 1464.28 and this pesky 0.I, but it's still correct. So collecting, we have I1, I2, we have this integral of 1/4 plus these other ones. And it turns out that this 1/4, or 1/4y, because it's all multiplied by y, is an elliptic function directly. And we call this I3. And this turns out to be elliptic f. This should cancel, but we're sort of abusing the range. Right now it's 5 and 7, so we're way outside the arc sign, which you can do transformations to alleviate, but that'll take us too far away. So now we have integrals of the form 1/x minus d times y, and where y is this quartic square root of a quartic. So let's do just these integrals. If we, again, all of our integrals, all of these particular types of integrals are actually pretty nice because we don't have to move the roots around. All of the roots of these are, in this particular example, are to the left of this integral, so everything works out pretty nicely. But you could do some transformations to move this around. So let's just, but we don't have to do that in this case. Let's multiply on the top and bottom of this expression by x plus d. And when you do that, you get a power, a quadratic on the bottom, and x plus d. It turns out that the linear part of x is integrable, and you get a tanh part. So we have to remember this. Each one depends on d, so we have to put that into each integral. And then the other one, which is d, the other integral, which is d over this, it turns out to be an elliptic pi function directly. So that's very nice. And again, we could manipulate this to get it into a better form if we want, but you need to check. So here are the two. So here are the integrals. So remember, there's this part that comes from the linear part in x. That's an integral that's integrable, and then here's the elliptic pi, and this is for each d, which was the root. And this needs to be evaluated at each r1, r2, and r3 and r4. So the full integral is I1 plus I2 plus I3 plus these four integrals, which again are the alpha i's come outside, so you just get this full term, alpha 1 plus alpha 2 plus alpha 3 plus I1 plus I2 plus I3 plus alpha 1 times I41, where the I41 are the expressions for the integrals of this form. Okay, so this is the full integral. If you evaluate it, you can see evaluate at the max minus the minimum point. At the endpoints, you can see that it's 0.146428, which is the same, plus a very small imaginary component, which will go away if you do these transformations that I was talking about. You can even evaluate it at the top limit and the bottom limit, and they add together, and the imaginary part will cancel out. And if you do different transformations, you will have either no imaginary part or some imaginary part, but the numerical integral should always come out to be the same expression, which is 14.146428. So here's the final result. If you put all of this in, you get that the symbolic form for the integral, for this integral, is given by this expression, which is beautiful and long. But that gives you an idea of how to do this simplification. One last thing I wanted to show is that if you plot this, it looks perfectly fine on our limit between 5 and 6. There's an imaginary component, and everything looks fine from 5 to 6. But if you look at a larger range, you can see that there are all sorts of problems, and they're not problems. They're just ways to interpret the elliptic integrals. So you need to do transformations if you are crossing these boundaries. Remember, these boundaries are at the roots of some of these expressions, so you can move these roots around so that you have nice boundaries from where you want to integrate for your particular case. So if you may need to move them, but this gives you, I mean, I knew this is a kind of a ridiculously long tutorial, and it gives you an expression that I don't know how useful it is, but it gives you an analytic expression for this integral that Mathematica couldn't come up with, but you can tell that it's going to be an elliptic integral. So I hope this has been of some use to you so that you can be a little less afraid, maybe, of elliptic integrals and can try to, if you encounter them, you can identify them and perhaps even resolve some of them and have fun. All right, bye.